Thank you, Stefania, and good afternoon to everyone, or morning or night, depending on where you are. It is my real pleasure to introduce today's speaker, Professor Keith Olive from the University of Minnesota. Professor Olive received a PhD in physics.
I want to say.
Sorry, somebody was unmuted. Okay. So it is my real pleasure to introduce Professor Keith Olive from Minnesota. Keith received a PhD in physics from the University of Chicago, and after doing research at CERN and Fermilab, he joined the faculty at the University of Minnesota, where he holds a Gloria Becker-Lupkin Chair in Theoretical Physics. His research lies at the interface between particle physics and cosmology, and if you work on these areas, or even if you touch them marginally, it's very common to encounter his name because he gave seminal contributions to several aspects of astroparticle physics, among which there is Big Bang nucleosynthesis, dark matter, baryogenesis, and inflation. He was one of the first to provide these seminal contributions, but as we will hear today, is continuing to explore these aspects. And in particular, today, we will hear about Big Bang nucleosynthesis post-Planck. And in particular, we will hear about the impact of new nuclear cross-section measurements and the implications for new physics. So I would like to thank Keith for accepting our invitation, and feel free to begin whenever you're ready. Thank you.
Okay, well, thank you for that very nice introduction. It is morning here for me. It's 10 in the morning. I'm not sure how. I'm happy to take questions during the talk. I don't know if there's an easy mechanism, if people can unmute themselves or do. I see there's some things in the chat, but I'm not sure how.
So I mean, if people have questions, they can either raise the hand or they can type the question in the chat, and I will make sure to report the question to you during the talk. Then, of course, at the end, we can have a discussion. Okay, great. So indeed, I'll be talking about just the current status of nucleosynthesis. And I was told that the audience is not specifically expert in the subject, so it will be a fairly broad and general introduction as well. Things in particular that I'm going to be highlighting are the connection between Big Bang nucleosynthesis and the CMB, and in particular the impact of the measurements of the microwave background anisotropies and their determination of the baryon density, which is omega BH squared, or our notation typically in BBN is the baryon to photon ratio, which is eta. And I'll also be talking about well, obviously the predictions of Big Bang nucleosynthesis, which predicts the abundances of the light elements, deuterium, helium, helium-3, helium-4, and lithium-7. And I'll discuss that in connection with the observations of those elements. And then, as Francesco said, I'll be talking about the impact of some new cross-section measurements, particularly that involve deuterium. And we'll see how that the importance of those measurements, and that hints at some other measurements that really should be taking place. Then I'll move on to constraints on particle properties, and particularly the constraints on the number of neutrino flavors, and which can then be expanded to constraints on beyond the standard model physics in general. And then if there's time at the end, I'll talk a little bit about the future CMB measurements and how they might impact BBN. Okay, now, oh, okay. So just to back up, where did all of this come from? Usually, oh, and I went too far. There we go. It usually, so I gave my punchline a little bit away, but it's okay. A lot of the credit for the initial phases of Big Bang nucleosynthesis, oh, maybe I didn't. Maybe it's this. It started from the group of George Gamow.
and that's and together with his graduate student Ralph Alpher and postdoc Robert Herman, they sort of laid down the foundations for what we know as Big Bang cosmology today. And in particular, that came from their work on trying to develop a theory to explain the element abundances in the universe. To start with, they weren't particularly concerned only with the light elements. They really wanted to understand the origin of all the elements. And really, Big Bang model traces itself back to these three. However, usually the work gets associated with these three authors, Alpher, Beta, and Gamow, and you can see already the wit that Gamow had in picking these three authors. Well, Alpher was his student, and he realized that if he could get Beta to co-author the paper, they would have a paper which was Alpher, Beta, Gamow. When I was a student, I had the opportunity to meet Beta. He came to the University of Chicago to give a colloquium, and he told us the story about this paper. He actually had nothing to do with the paper. He said that Gamow sent him the paper, asked him to be a co-author. He said he read the paper. He said he saw he didn't see anything obviously wrong. Those were his words. He didn't see anything obviously wrong with the paper, and so he agreed to co-author it. And so it's a famous paper, and so that's in Physical Review, Alpher, Beta, Gamow, the origin of the chemical elements. And so what they were trying to do was to have a theory that would predict the element abundances. And so the element abundances were more or less known, and they came up with a theory. Here they seem to explain it reasonably well. They don't get the peaks and the valleys, but the theory didn't, today you wouldn't say that theory made any sense. It was largely starting with neutrons, a universe filled with neutrons, and looking at neutron capture. So they had some equation that they tried to solve, and this is the result of that. What we try to do, of course, is these are the current abundances of the elements. Of course, most of this has nothing to do with Big Bang nucleosynthesis, as we know now. Only the lightest three, hydrogen, helium, and lithium, originate in the Big Bang, and even not all the lithium comes from the Big Bang. Lithium, beryllium, boron are also produced in cosmic ray interactions. And then all the rest come from stars. So it's, and that's fairly well understood, that in fact, the failure of BBN to explain this led to stellar nucleosynthesis. So the connection with the CMB also originated from Alpher, Herman, Gamow. Actually, as I'll just show you in a moment, from the work of Alpher and Herman. Gamow wasn't actually on the paper, but they made the prediction that there should be a CMB, and the argument is very simple. If you've never seen it, it's remarkably simple. It's all right here on this slide. In their theory of the Big Bang, they required only that the temperature was larger than about 100 keV. And that's so that you could have the nuclear reactions take place and form heavier elements. In their theory, that temperature greater than 100 keV corresponded to a time scale less than about 200 seconds. Okay. And they knew something about the cross-section for producing deuterium, P plus N to deuterium plus gamma. Sigma V was about 5 times 10 to the minus 20 centimeters cubed per second. And that implied that a particular density of baryons. They were thinking neutrons, but neutrons, protons at the time. And so if you just assume that NB is 1 over sigma VT, then you would say you need about 10 to the 17 baryons per cubic centimeter. And then you can estimate what the baryon density is today just by counting galaxies. It's about 10 to the minus 7 per cubic centimeter. And if you realize that the baryon density just scales with the volume, and if the volume scales inversely with the temperature cubed, NB goes as T cubed, And that's enough to then predict the temperature in the universe today. And that's just the cube root of the ratio of those densities. And that would give you 10 K. So that's an extremely rough estimate, but actually not that far off, would you think about it. Alpher and Herman did much better than that. Okay, so I get a little delay sometimes, but so this is the paper by Alpher and Herman from 1948, and they said if you know something about the matter density and the radiation density early on, and you know something about the matter density today, which is exactly what I was referring to, that gets you a value for the radiation density today. And I always find it amusing when I see the little phrase that follows that, the present radiation density, which is perhaps the least well-known quantity. Of course, today it's by far the best known quantity due to the extremely accurate measurements of the microwave background. But they then made this estimate, and they said it corresponds to a temperature of 5 degrees. So they did better than my little back of the envelope calculation of 10 degrees. They said it's about 5. But actually, they didn't stop there. They said, well, we understand that there's some uncertainties. And so they say, we want to see how the results are sensitive to the choice of densities. And then so they take another choice and they say, well, it could be that it's 1 degree. So when you think about this, in 1948, they're saying that the temperature should be somewhere between 1 degree and 5 degrees. This is really remarkable. And that all came from their theory of Big Bang nucleosynthesis. Of course, now we know, if you jump ahead to the last Planck results, not only is the temperature, well, the temperature was really determined already very accurately by Kobe, but the anisotropies in the microwave background are extremely well measured. And that leads to a determination of the baryon density. So rho b, omega b is the ratio of the baryon density relative to the critical density. H is the scaled Hubble parameter, and this is the value determined by Planck, and that corresponds to a baryon density in units of 10 to the minus 10 of 6.12 plus or minus 0.04. So that's the main parameter that we use in nucleosynthesis. So how does nucleosynthesis go? Well, again, starting in the early universe with at least temperatures bigger than an MeV or so. That was the 200 keV I had on the other slide. Assuming that the universe is dominated by radiation, so it's just black body, and you can just count the contributions to the radiation density. The 2 is for photons, 7/2 for electrons and positrons, and 7/4 times the number of neutrino flavors. The funny number there is just the difference due to Fermi and Bose statistics. And then eta should be on the order of about 10 to the minus 10. And beta equilibrium is maintained by the weak interactions. And this was the point that was missed early on. Embarrassingly, there was some work by Fermi that also missed this point, that you had the beta equilibrium was good in the early universe. And so with equilibrium, that tells you what the ratio of neutrons to protons are. So if you have all of these interactions in equilibrium, the ratio of neutrons and protons is just given by the small mass difference. So it's almost equal to 1 at temperatures larger than an MeV. These interactions freeze out because the fact that the universe is expanding and the Hubble rate of expansion goes as the temperature squared, whereas the weak interaction rate goes as T to the 5th. If you think about it, the mean time between interactions is 1 over gamma. The age of the universe is 1 over h. And so basically, as time goes on, the mean time between interactions slows down so that the interactions take place, the next interaction takes place outside the age of the universe. So freeze out then fixes the neutron to proton ratio. And then, of course, you can't stop neutrons from decaying. So there's still some extra neutron decays, and that drops this ratio from about a 6th that freeze out to about a 7th at the time of nucleosynthesis. Nucleosynthesis doesn't start right away. You might think it starts when you get to a temperature equaling to the deuteron binding energy, EB, which is about 2 MeV, but that doesn't happen. And that's because the baryons are sitting in a huge bath of photons. And even if the photon energy drops below EB, there's still a tail of that distribution. Remember, the density of photons relative to the density of baryons is about 10 to the 10. So you can go pretty far out in that tail, and you're still always going to be destroying deuterium. So you have to wait until the rates of production and destruction are about equal to each other, and that happens only when the temperature falls to about 0.1 MeV. So that's about a 20th of the binding energy of deuterium. If you make the assumption at that point that all the neutrons that you have left over, so remember, neutrons are decaying while you're waiting. Some neutrons are decaying all the time. But so at a 1/10 of an MeV, you have about a neutron to proton ratio of about a 7. If you plug that into this simple estimate, if all the neutrons go into helium-4, you would expect about 25% of the mass fraction in helium-4, the mass fraction to be in helium-4. And then the remainder is in deuterium, helium-3, and lithium-7, but those are very, very small numbers. So to make the calculations in nucleosynthesis, you have to put together a chain of reactions, starting with neutrons and protons at the bottom, making deuterium, helium-3, tritium. And you see a lot of the roads go to helium-4, being one of the most stable of the light elements. And then there's a gap at A equals to 5. So helium-5 is extremely unstable. And so it's very, you can't build up an equilibrium abundance of helium-5. And so you have to cross over directly to 6, which becomes difficult. You can make some lithium-6, some helium-6. You don't make very much. Helium-6 is also unstable. And then you make some A equals 7. In fact, in BBN, we talk about lithium-7. Beryllium-7 is unstable, but actually in the Big Bang, you really are making beryllium-7, which decays much later. It's a electron capture decay, and since you don't have any neutral beryllium-7, it actually hangs around much longer than its lifetime might suggest. And then it decays to lithium-7, which you observe today. There's another gap at 8. This thing shows the lithium-8 and boron-8 are stable, but they're stable on laboratory standards, but not on Big Bang nucleosynthesis standards. So there's another gap here, and essentially nothing gets produced. Beyond mass 7. Of all those reactions on the previous slide, there's only really about 12 of them that are really important, that really determine the final abundances, and those are listed here with some examples of what those cross sections look like. Some are better measured than others. The reaction B here, you see, this is an old plot. I'll show you a newer one a little bit later. This is an old plot for the DP gamma reaction. So that's deuteron plus proton making helium-3 and emitting a photon. You see, it's not very well measured here. This is even a log plot, and so quite a bit of uncertainty in that. This is one that has been remeasured by the Luna collaboration. I'll get to that in a little while. So as I said, BBN couldn't explain the pattern of abundances despite what alpha, beta, and gamma have tried to do. And then, as I said, that also led to a new field, which was stellar nucleosynthesis. And so people sort of abandoned BBN, but there were still some questions that remained. And that is, how do you get 25% of the mass in helium-4? That's pretty much agrees with observation. Stars do contribute helium-4, but only at the level of maybe 2, 3, 5%, not 25%. And where does the deuterium come from? Since we observe deuterium is only destroyed in stars, and through the process of chemical evolution, deuterium is pretty much monotonically decreasing. So how do you actually make any deuterium that can be observed? And those questions led back to the resurgence in BBN. which could account for the abundances of these elements. So as I said, the predictions, you put all those reactions into a code, you put it in the context of an expanding universe, you have a standard cosmological model. And here I'm plotting things in terms of the parameter, which is the baryon to photon ratio. And you have the abundance of helium-4 by mass and the abundances of deuterium, helium-3, and lithium-7 by number. Basically, this part is actually beryllium-7. This is really lithium-7 here. Now, as I said, WMAP and Planck have pretty much fixed the baryon density. And so that's the value of eta, and the thickness there is also its uncertainty. So it's pretty well determined. So there's really, in standard Big Bang nucleosynthesis, there are no free parameters. Previously, we talked about the neutron mean life. I'll say a word about that a little later, but that's very well measured now. Number of neutrino flavors, well, if you take 3, as in the standard model, then that's it. This is all you have. And I'll talk about variations to that later on. So you can just read off the predictions of nucleosynthesis and then compare them directly with observations. Just a word about the uncertainty. So the thickness of these lines actually corresponds to the uncertainty. If I remember, I think the helium is actually a 3 sigma uncertainty, and these are 1 sigma for the others. But that's easier seen here, where I'm showing directly the uncertainty, the relative uncertainty in each of the elements. And these uncertainties come mainly from the cross-section measurements. And you see the uncertainty in helium-4 has been multiplied by a factor of 10, just so that you can see it on this plot. So let me say a word about the observations. So just broadly, helium-4 is observed in extragalactic H2 regions. These are regions of ionized hydrogen gas in other galaxies. It has abundance by mass, as I said, about 25%. Lithium is observed in the atmospheres of dwarf halo stars, so stars in our own galaxy, old stars, low metallicity, and the abundance is about 10 to the minus 10. Deuterium is best observed in quasar absorption systems. So looking out in the direction of a quasar, looking at a gas cloud between us and that quasar. This quasar serves as the light bulb, and we're looking for absorption of that light in these gas clouds. And that leads to now very accurate determination of the abundance, about 3 times 10 to the minus 5. Deuterium is also observed locally. You can infer its abundance in our galaxy, in our solar system. Of course, all of that carries the uncertainty as to how much deuterium has been destroyed since the Big Bang. Similarly for helium-3, that's mainly observed in the solar neighborhood and the interstellar medium. It's also at about 10 to the minus 5 by number, which is actually in pretty good agreement with what you would expect from nucleosynthesis. But again, you have the same problem. Helium-3 is produced in stars, it's destroyed in stars, depending on what the mass of that star is. So you have to think that you understand the chemical evolution of helium-3 to be able to use those abundances. And I won't talk about helium-3 any farther. So deuterium, as I said, it's only destroyed. So all the observed deuterium is actually primordial. Any deuterium that we have actually came directly from the Big Bang. And as I said, it's observed in the interstellar medium, and you can infer it from meteoritic samples. But the best observations come from these quasar absorption system. This is a selection. There's about 11 objects now, 11 or 12 objects where it's observed with relatively good, with relatively low uncertainty. This selection is taken from a paper by Cook et al. So as I said, it's coming from an absorption line spectrum. You're looking for the little wing in that spectrum due to the isotopic shift. And this is from some older work by Teitler et al. So it's not an easy measurement to make. And if you go back several years, this is what the abundance data looked like. It's not bad. I mean, the observed abundance there was about 3 times 10 to the minus 5. The big BBN prediction, about 2.6. some uncertainties. Wasn't too bad. Maybe there looked like there was a little bit of destruction. Destruction in the sense that there's a lot of dispersion here. So this data was actually fairly hard to understand given the error bars here. But more recent measurements, and throwing out the older data, the recent measurements look like this, which is really quite good. The error bars are very small. The data is very uniform, and that the line there is a fit to that data. So now you're in a situation where the prediction from BBN, which is also improved in the last several years to about a little over 2.5 times 10 to the minus 5, and the observational average, where the uncertainty has dropped dramatically. So now BBN is actually behind the observations, and that's one of the reasons that Luna measurement is so important, because that goes into dropping this uncertainty. And I'll come back to that a little later. But there's still some residual uncertainties that require new cross-section measurements. So if we go back to this plot, so now I put in the line that's the average of the observed deuterium abundance. And if I now superimpose that with the Planck density for the baryon density, this is really rather remarkable. Right, so you have the prediction, you have the observation of the deuterium abundance, and the observational determination of the baryon density, and you get a fantastic agreement. So when people talk about the agreement between BBN and the CMB, this is really what they're talking about. These three lines crossing essentially at a point. So let me move to helium-4. Helium-4 is also predominantly primordial. This is a little bit this is an old plot, but this is an exaggeration plot. There's no error bars here. The point here is that over a wide range of, in this case, I'm using oxygen abundance as the metallicity tracer. The solar oxygen abundance is out at about 450 in these units, so it's way over to the right. And if you fit this data, you essentially almost a flat line, and the intercept here should correspond to the primordial abundance. Okay, this only happens for three elements, actually: the deuterium abundance, which I showed previously, helium, and lithium. All other elements, and here's an example. If I plot the nitrogen abundance in these same galaxies, same ones that we see the helium in, as a function of oxygen, you see the pattern is always that it goes towards the origin. That is, when the oxygen abundance is 0, the nitrogen abundance is 0. If I did this for any other element other than the three coming from the Big Bang, this is how it would look. Because before we have stars, we don't have any of the other elements. These are all produced in stars. So the oxygen abundance is produced in stars, and so is the nitrogen abundance, and so they're correlated. Then you can argue a little bit about whether this is primary production, secondary production, but point is that it's not Big Bang produced. Helium is produced from emission lines. So you have an emission line spectrum, which shows you the abundances of a number of things, but also a number of helium lines here, some strong, some not so strong. And from those emission lines, you can get an abundance. However, it's not quite so simple, because when you really get down to it, there are a lot of parameters that go into some model. You need to have a model. You don't observe the abundance, you observe a flux coming from those emission lines. And what you can do is you use a model which involves a number of parameters: electron density, helium abundance, underlying absorption, optical depth, temperature, collisional, the abundance of neutral hydrogen, which is responsible for collisional corrections. You put all this in, and you can calculate a predicted flux given these parameters, and you can compare that to the observed flux. So lambda here is each of the helium lines, and relative to H beta, which is a reference line. And the trouble is that there are a lot of degeneracies, and here I show one of them between the electron density and the temperature. So you have a fit, which gives you, say, either 68 or 95% confidence level contour in this plane, but that corresponds to a very, very wide range in helium abundances. These helium abundances here are by number. And so I put up here in sort of big numbers here, the abundance by mass. So you're going from about 23.5 to 25%, which is far from being precise. This is not the way it was done in the past. In the past, basically, all these parameters were just fixed, and you didn't worry about fitting them for each object. So these were all fixed, and you would have, 3 lines basically that you would compare, and then you would just average the helium abundance for each of those lines, and that would be your claimed helium abundance. And that ignores all these degeneracies. So if you go back 10, 15 years, the helium abundance data looked much better than it does now because you just essentially ignored all the uncertainties. Now, not each object and not each measurement is equal, and sometimes these objects give you pretty nonsensical results. It's still not completely clear why that's the case, but here's an example which is quite horrible. There are basically 9 to 10 observables depending on the object you're using, and you're trying to fit 8 parameters. That gives you 1 or 2 degrees of freedom. That means that when you consider this chi-squared statistic, you expect a number, you'd really like it to be around 1, probably not bigger than about 4. And some objects are just terrible. They give you a chi-squared of about 20 for 1 degree of freedom. That's, as I say, that's nonsensical, and it also doesn't give you a good determination of the helium abundance. However, others are really quite good. So here's an object where the helium abundance is measured. Whether this is a problem with the data or a problem with the model, or the problem with the model, on each object is still not completely understood. There have been a lot of improvements to these models. The new emissivities have been employed. That's in 2013, adding a new line that got you up from the 9 to 10 lines, giving you 2 degrees of freedom. And most recently, we've come back to it and argued that one should be really adding a whole bunch more lines. We had 2 helium lines and 9 hydrogen lines, because really you're trying to get a ratio of helium to hydrogen. So you need to know the hydrogen as well. And that gives you 21 observables with 9 parameters to fit. And that's really, we looked at one object for that, and this is this past year. We had looked at that several years ago. That was, again, using 1 degree of freedom, 9 lines with 8 parameters. The chi-squared there that we found was about 3.3. That should be compared to 3.8. So that was okay. But adding all these lines, now our chi-squared, of course, is much higher, but our 95% confidence level is 21. At 1 sigma, it's about 13. So we're actually closer to 1 sigma now. And if you just notice, you don't have to look at all the numbers or what these quantities are, but you just look that the uncertainties have dropped dramatically. So it's a much better fit. And the final helium abundance, well, the abundance didn't change much. The uncertainty dropped by a factor of about 3. And that's what we're looking for, is to really try and get these uncertainties down. This is the existing, our sample of existing helium abundance data. And this includes this new point here. Leo P is a dwarf galaxy in our local group. And the abundance now, the uncertainty dropped by, just from that 1 point, already dropped from 0.004 without that point to 0.034. So it's definitely going in the right direction. Since then, we've added 1 more object. The uncertainty is quite large in that object, but it's a very low metallicity and serves as sort of harbinger of perhaps more data in this direction. And things didn't change much with that 1 point. Uncertainty dropped a tiny bit again. There are some other groups that have looked at this fairly recently. Xu et al. They get a number very similar type error, and Karuchin also. They're using SDSS data, so it looks like they have a real lot of data here, a lot of uncertainties in that data. One could argue whether or not you should really be using a lot of this high metallicity data, because in the end, you're doing some sort of linear extraction. You don't really know that it stays linear out to high metallicity. And so their uncertainty is smaller, but that uncertainty is really just due to numbers. It's due to the large number of points. The actual value is very similar as well. As I said, the neutron mean life is always a concern. This is sort of this is a plot of the accepted value of the neutron mean life as reported by the Review of Particle Physics, particle data group in 1960s, 70s. It came down quite a bit and it's had a couple of little quantum jumps, but it's really quite stable. The error bars here are smaller than the dots that I'm showing. So it's not varying very much. And here you can see a little bit of how much the helium abundance changes when you change that neutron mean life. But for now, we're taking that to be fixed. It's 879.4 with an uncertainty of plus or minus 0.6. And so that also gets folded into the uncertainty, calculated uncertainty in the helium abundance. So this is how helium looks. And so again, the uncertainty in the observations is too large. It's the best we can do right now. It would be nice to get this smaller, but it's certainly consistent. And that brings me to the uncomfortable element, which is lithium. Is some old plots showing the lithium abundance. Here, the notation is the bracket of lithium is the log of the lithium abundance plus 12. So 2 is 10 to the minus 10. And this is showing as a function of the surface temperature. And what you're seeing here is pretty much what you might expect. That is that the lithium is destroyed at lower temperatures where the convection zone is thicker and reaches up and can destroy some of that surface. The surface abundance of lithium, which is what we see, gets exposed to the hotter interior, and so the abundances are lower at lower temperatures. Higher temperatures, that convection zone is very thin, and the abundance of lithium is preserved. So you expect this to be the primordial abundance, and this is known as the Speet Plateau for Speet and Speet, who first saw this in 1981, 1982. And here's the same plot, same data, just shown as a function of metallicity. Here, the stars are all higher than at 5,500. Again, now at higher metallicities, you need to go to even higher temperatures. So here you see the effects of destruction of lithium. And again, that plateau pops out. Here again is that plateau, a little over 10 to the minus 10, but this is the prediction of BBN. And now at high metallicity, so the solar abundances are higher, but there are other processes that come in, cosmic ray production, that's what's shown by the diagonal lines here, also production of lithium in nova. Our problem is down here where there's a mismatch. And there's been a lot of study about this. I'm not going to go into detail. Is there a problem with the nuclear rates? A number of people have studied this. It's very hard to change the nuclear rates because now these are the same rates that are going on in the sun. And these are restricted now by the solar neutrino flux, and there have been other cross-section measurements. None of this actually works. We've looked at resonant reactions, whether or not there was just some missing reactions that could have destroyed some of the beryllium-7. So, the resonance, if there was a resonance at 15 MeV, that could have cured the problem, but that wasn't seen. Stellar depletion, there's always been argued against stellar depletion because of the lack of dispersion in the data. Standard stellar models predict very little dispersion. You could create models with turbulence, rotational destruction, and there you could have much more destruction. Dex is units of log units. And also lithium-6 abundance was observed in a couple of stars. And then if lithium-6 is there, then lithium-6 is very easily destroyed. And so if lithium-6 is there, then the lithium-7 shouldn't have been destroyed. I'll come to this in a second. The lack of dispersion is no longer clear. And the lithium-6 abundance is now being disputed even in those two observations that date back some 30 years or so now. Lithium abundance data is evolving, I should say. It seems that it's no longer so uniform once you get down to very low metallicities. And this is not very well understood. And here's another example, 2018. This doesn't look like a plateau anymore. A lot of these things are upper limits, which are signs that the lithium has been destroyed in these stars. And here's probably the most recent paper showing lithium abundance. So it's not clear. The primordial abundance is here, but this is what you would expect if you have destruction of lithium in these stars, that you don't get a uniform abundance, but some stars destroy it by a factor of 3, some by a factor of 4, some by a factor of 5, some by a factor of 10, and maybe that's what we're seeing. There have been a lot of other studies, whether it's stellar parameters, and then you get to more exotic things, decaying particles, axion cooling, variable fundamental constants. I'm not going to go into any of them here. So we can now start looking at more detailed comparisons between the theory and observations and form likelihoods for the observations. Those are the ones that are shown as yellow. We can look at just the CMB alone. That's only shown here for helium-4 by the cyan curve. And then the combination of CMB and BBN where you convolve these likelihoods, and that's the purple. And this graphically, you see right away what's going on. Helium matches very well, but the observations are somewhat uncertain. Deuterium looks really good. Lithium looks really bad, and there's no observation that I can match to helium-3. And this is just some numbers that are there if you can look at these slides later. Now, the deuterium has, as I said, got a little bit of boost in terms of our understanding from this LUNA measurement of the DP gamma reaction. So that data that I showed before was very sparse here. The LUNA observations, if you can pick it out on your screens, are these red points and so they're right here, right exactly in the range that we want them for BBN with relatively small error bars. And so this is really a huge bonus for the BBN calculations. The black curve, I think, is our fit to LUNA data together with other data. One of these is the LUNA. I think the red dashed one is the LUNA fit to their own data. And since their data is by far dominating all the other data, since it's all there and with small error bars, those fits are very, very similar to each other. Our old data was the blue dotted. You see, it's not very different, which is good. So the LUNA data basically confirmed the previous fits, but now to much higher accuracy. What they did is sort of dispel the notion that there was some theory problem. Well, there might be a theory problem, but there were a number of groups that were using the theory. Oops, sorry. And now I went the wrong way. And I'm going the wrong way again. Okay. Was using a theory calculation saying that, well, we don't have good data in the BBN range, we'll use theory, and that predicted a higher cross-section and led to deuterium destruction and actually led to some discrepancy between theory and experiment. And LUNA has actually restored it, if you want. And here's a plot a little bit broader in energy and showing something similar to what I showed before. The LUNA plots are LUNA data are these really tiny points here. So this is really a big bonus. The mean deuterium abundance didn't change very much. Did drop a little bit because their data is a tiny bit higher. The theory, if you use the theory cross-section, that would be quite a bit lower. And this is LUNA's estimate, this is our estimate, and the uncertainties are similar. So the uncertainty came down from about 0.13 to about 0.11. You might think that's not that great. Well, it is. It's really quite good. Problem is that there are two other cross sections involving deuterium, DDN and DDP, that also carry now the largest uncertainties, and they're what's responsible for those. So if we can get LUNA to do some more cross-section measurements, that would be great. The uncertainties did drop. This is like an early slide that I showed before. The uncertainty in lithium drops a bit. Uncertainty in deuterium drops. So here you see visually what the Luna observation did. And of course, helium doesn't change with this. So let me come back to the connection with CMB. So you can get just what we did is we took the raw Planck data. Planck, when they talk about their data, they actually put in some BBN, although they provide their likelihood chains without any assumption about BBN. That is, they use the relationship between helium and the baryon density in the results they put in their papers. But they do provide that, so if you don't want to use that, you can get just the Planck determinations of the baryon density and their determination of the helium abundance without assuming BBN. So it's even amazing that they can do that. And the left shows the older Planck results, the newer Planck results here at the bottom, Planck 2018. And then also if you allow the number of neutrino flavors to be variable, this is what they get. So they don't get very precise helium abundance data, but they do get something that is actually not so terrible without using any BBN. So we can also now just determine the likelihood functions for the baryon density. BBN with just helium abundance does a terrible job. I don't show a large enough range in the baryon density to see that this is actually a distribution. You just see this thing being very, very wide. Deuterium does much better. That's the blue dotted. CMB, of course, is what's really driving everything, and that's the red dot dash curve. So that's the CMB only determination of the baryon density. And now you can combine that with BBN, and you get that to be a little bit slightly different, but and slightly better. And then these are the numbers depending on what sets of data, BBN, CMB with or without CMB, etc. And so this would be our baryon density, all putting everything together. That gets altered a little bit with the Luna. So it's, as I say, the Luna measurement is not trivial. It doesn't change things a lot, which is good. You actually don't want things to be changing a lot because you should start worrying if they do change a lot. So in the last few minutes, let me come to the idea of allowing or using BBN to set constraints on particle properties. And the way that comes about goes back to the very early slide that I gave you, sort of the rundown of how BBN works. And that came to do with the balancing of the weak interaction rates and the Hubble expansion rate, which is going as t squared, whereas the weak rate was going as t to the fifth. Now, if you change anything on either side of this equation, you're going to change the value of the temperature at freeze out. That's going to change the value of the neutron to proton ratio, and so forth. So H is given by the density, the radiation density, which, as I said early on, had to do with the number of neutrino flavors. So if you change N nu, you're going to change H and you're going to change TF. And that will change the neutron to proton ratio, and that will change the helium abundance. So how sensitive is it? Here is the same plot. The green lines are the N nu equals to 3. So a standard model. Blue is N nu equals to 2. The red is N nu equal to 4. So helium, you see, is very, very sensitive to changes in the number of neutrinos. Now, deuterium, you say, well, it's not very sensitive, which is true, but the deuterium measurement is very accurate. So, whereas the helium abundance is less accurate. So even though the sensitivity to N nu from deuterium is not great, the fact that it's so precisely measured restores that. And lithium, well, there's nothing you can do with lithium because you don't have that agreement. And now if you, in the end of the day, you come to the conclusion that the lithium has been destroyed in these stars, we don't actually have an observation of primordial lithium. So here are the same likelihoods now where you allow the number of neutrino flavors to vary. Now the well, basically what that does is that will move things down so that you get good agreement between the observation, a better agreement, I should say, between the observations of helium and between the prediction and the observation. You remember now the prediction for helium used to be extremely narrow. Now it's broad, because if I allow the number of neutrino flavors to vary, well, I can get a much broader range in helium abundance, and I can get that to agree nearly perfectly with the observations. Other things don't change quite so much. Here, if I plot the predictions, CMB only and CMB with BBN for the number of neutrino flavors as a function of baryon density, so no abundance data taken into account here. So CMB already does fairly well. CMB only, although it would allow you up to about 4 neutrino flavors. Just putting in the relationship between helium and the baryon density already does significantly better. If I now start adding the observations, here's what I would get for helium. So the helium, BBN and helium alone are these sort of horizontal lines. Remember, they don't close here because they would predict a much larger range in the baryon to photon ratio. But as soon as I add the CMB, this is now my prediction for the number of neutrino flavors. Deuterium is now diagonal. So if in the standard model, that would close, that would give me a nice range for the baryon density. But if I allow the number of neutrinos to vary, they are also open, but they're not degenerate with helium. So as you see in the next slide, they'll combine. And here, if I use deuterium and helium for just BBN, I get the wide contours. And again, when I add the CMB, I get something that's quite tight. So these are the results now, again, for the baryon density, because they'll be a little bit different if I allow the number of neutrino flavors to vary. This is now the prediction. You can look at the bottom line prediction is 2.84 plus or minus about 0.15. And whoops. And that gives you 95% upper limit of about 3.15. Again, the standard model is 3. Now, I should say a couple words. First of all, if you're worrying about fractional neutrinos, I mean, you think that neutrinos only come in integer values. Of course, you could have other weakly interacting particles which may have decoupled early in the universe. They would contribute a fraction of a neutrino. That's where that fraction comes. That is because at the time of nucleosynthesis, they might have a different temperature than the neutrinos have at that time. So you could get fraction, and this is where you get constraints on models beyond the standard model, because if you start adding new degrees of freedom, which would be present at the time of nucleosynthesis, they become, and they're relativistic, they become heavily constrained. I should also just point out, if you're a little bit expert, the n nu here I'm talking about is really the n nu. So this 3 is 3, whereas for the CMB, that would correspond to an effective of about 3.04 because neutrinos don't completely decouple. But these numbers are all relative, have that factored into account, and this is really the number of neutrinos. There's a little bit of an effect due to Luna. They actually get you a little bit in the right, move you a little bit in the right direction. It's not significant. And that upper limit now is about 3.17. What about the future? Where does the future portend? The next round of CMB experiments, labeled S4, is expected to do significantly better on the helium abundance. This is a factor of about 3 or 4 better in the determination of helium alone from the CMB, not using BBN, but just coming from the CMB. And also just the CMB determination of the number of neutrino degrees of freedom here, 0.09. And what that does to these things, so here I'm assuming that the central values don't change. This is again the BBN prediction of helium-4. There's the observation that cyan here was the CMB only determination of helium-4, and what we can expect from S4 is going from the cyan to the blue. Okay, again, maybe things will overlap better. That's to be determined. And this is, the others don't change that dramatically. For the number of neutrino flavors, again, what you would get is this is the current Planck 2018 determination. CMB only is again that blue dashed curve, and with S4 that would become the dashed curve here, and you can see it's markedly thinner here. The uncertainty would be greatly reduced. So this would provide again very, very strong constraints on physics beyond the standard model. So I think I'm just about on time. So BBN and CMB, as I said, broad conclusion is they're in an excellent agreement. As I say, that is quite dramatic with the case of deuterium, and I would say good, maybe excellent is an exaggeration for helium-4. We'd really like to get those observations better for helium-4. Lithium-7 is problematic. The BBN abundance is high. That's not new. What is newer is the fact that it's not quite so clear anymore that the lithium observations are in fact primordial. There seems to be a lot of dispersion. Granted, that's at lower metallicity, but we have now this funny situation where there's a lot of dispersion at high metallicity, well, high, above minus 1.5. And here, maybe I didn't say it, minus 1.5 refers to log relative to the solar abundance, and that's in iron. So minus 1.5 is, I guess, about a 30th of solar abundance. Minus 2 would be 1% of solar. So it seems maybe it's still uniform in that range from minus 1.5 to minus 2.5, but below minus 2.5, once you get to like 1,000th solar, the dispersion is back there. And so I don't know, I don't understand why it would only be uniform and why that little segment in metallicity would correspond to the primordial value. And then as well as new lithium-6 observations seem to only provide upper limits to lithium-6. And so that might be consistent now again with the fact that lithium-6 has been destroyed, opening up the window that lithium-7 has been destroyed. It's certainly not a position I've argued for in the past, but that seems to be where the newer data is taking us. Wish list. So we got great new data from Luna for DP gamma. Now I'd like to see the same thing for DDP and DDN. These are the two cross sections which dominate the uncertainties in the predicted values for deuterium. And like to see some new high precision measurements for helium-4. And I think we know how to handle those now. We just need to get to identify suitable targets and make those measurements. And maybe we can get the uncertainties in the observed determinations of helium-4 down. But overall, I think the standard model is looking good, which is not a real surprise these days. And we get very strong constraints on physics beyond the standard model. So I think I'll stop there.
Perfect. Perfectly on time. Thank you very much for this very nice talk. Very comprehensive, also with a nice historical perspective on BBN. Now we open the floor for questions. So in case people from the audience have questions, they can either raise the hand or just unmute yourself and ask the question right away. Let's see.
Can I ask you something?
Okay, please go.
Thank you. Thank you for the very nice talk, but I'm confused about something very trivial. So when you do the fit with the changing number of neutrinos, how should I interpret your results in terms of delta and effective? Because I'm slightly confused by the central value that you...
Right, so 3, 3 correspond. So when people talk about N effective, the standard model value for N effective is 3.044 or 044, right?
Yeah.
Well, people argue very vigorously about that third decimal place, which is great. So the numbers that I showed are 3, correspond to 3.045. So you scale it if you want that way. I'm thinking in terms of physical degrees of freedom rather than the effective degrees of freedom that is relevant for the CMB.
Okay.
Does that make sense?
Okay, can you go back to the slide where you?
Sure.
Sorry.
I don't know which, this slide or
this one. Okay.
So you should multiply this number by 3.045 divided by 3 to get the value of N effective. It would just scale that way.
Okay.
Right. But this is really, if this number was 3.000, that would be perfect agreement with the standard model. N effective. So I would have to multiply this, as I say, by 1.015, right, to get the effective number.
Okay.
That would also assuming, well, you have to be a little bit more careful because now if they're not neutrinos and they're decoupled earlier, then you wouldn't make that same multiplication, right? Because,
true. But does it mean that the neutrino temperature is slightly smaller than expectation? Because it's below 3.
It's a little bit larger, right? It's not even that it's so much the neutrino temperature. The end neutrino temperature is what it is. The point is that they haven't quite completely decoupled, right?
Okay.
So really during E plus E minus annihilation, it's just the unfortunate thing that E plus E minus annihilation happens at about the same time decoupling happens. And so you get
okay, sorry, yeah. Okay.
Does that make sense?
Yes, sorry. Okay, thank you.
Okay, we have a raised hand by Leandros. Please just unmute yourself if you can. I'm allowing you to unmute.
Unmute. Okay, thank you.
Please.
Yes, thank you for a very interesting talk. And I have a question about the slide you showed, the neutron lifetime. Could you please go back to that slide?
Oh, this one.
Yeah, there seems to be a several sigma drop at about 2010, because you said that the error bar is within the point. Is this an indication of some change in the experiment? I mean, could it also happen with the nuclear rates also in other observables? What happened between?
There have been, as I say, I did say there were a few quantum jumps in these measurements. It's a little. So first of all, these numbers are just the values reported by the review of particle physics. I did nothing to these numbers, and I'm not installing any of my personal expectations about which numbers are good and which numbers are bad. I'm just taking them straight from that review. Okay, you can say what you want about the old numbers. It was a little bit amusing to me that even around the early 1980s, there were already some reported numbers by some Russian groups down here. But the accepted values were always the high values, and these were by American and British groups. It wasn't until the French group led by Mampe that he got a number that was like the Russian groups. And then all of a sudden, the review of particle physics dropped the number to the French group. And that was, I think, these numbers here. Then there were more measurements, and then they came in down here. And so, yes, they're all low. There are two different methods for determining the neutron lifetime. And they are within themselves a few sigma off. And so there is controversy within that field as to what is actually the best neutron lifetime. And there are other reviews that are cited in the review of particle physics, which go into that in a lot of detail. But this particular jump, I don't really remember if it corresponded to a different method or one new measurement with a much lower uncertainty and discarding older measurements, which is I'm assuming is what happened, is that some older measurements got discarded in favor of some newer ones.
Okay, thank you.
But please look at the section in the review of particle physics. All the references are there, as well as a little bit of the discussion of the controversy, as well as a review which discusses the controversy in detail.
Yeah, the question is if this would happen also with other nuclear cross-sections. It would be interesting to see if there are similar things might happen.
This isn't really a cross-section, because this here you have to. The problem is you have to trap the neutrons and you have to count them, and so then it becomes a question of how you're actually doing that.
Okay, thank you.
Thanks. Any other question? While we wait, I have a quick question. Is there an intuitive way to understand why the helium abundance is so sensitive to a nu, but the other elements in the plot you show, where you had the prediction for the helium and the deuterium and the other light elements, when you were changing the number of neutrinos? You had here, this one. Yeah.
Yeah. It's basically coming from this, because the helium abundance is extremely sensitive to the neutron to proton ratio.
Okay.
You can get that dependence analytically. Usually in my class, I do it for you can get the delta Y, delta N nu analytically, because all you have to do is use this expression. And what you're doing is you're changing. So the H is going as the square root of rho, and so the square root of rho has the square root of n in here. You can then derive the new freeze-out temperature. You put the freeze-out temperature here. The neutron-proton mass difference is fixed. You can get a new neutron to proton ratio, and you plug that in here. So you can just take derivatives of all these things and trace it back. So the helium abundance uncertainty relative to the number of neutrino flavors is very direct.
So the reason is basically that almost all the neutrons are going to form helium. That's the reason. Okay. Thank you. Very good. Okay, we have another question by Sebastian. Please go ahead.
Okay, thanks. Do you hear me?
Yes.
Okay. I think I have seen this year some papers that were talking about a deuterium tension between CMB and BBM.
Right.
Do you have something to say about that? Because I think they're also using those Luna 2020.
Yeah. Okay. Very good. Let's see. I have to just remember where it is. No, it's before lithium. Oh, I did it first. Oh. What did I do?
You are not sharing the screen anymore.
Oh, because it quit on me. I must have gone too fast. Okay, let me try. Oh, I see. I lost my talk. I think I can get it back quickly. There we go. Let's see. Sorry about that. And now it's sharing again?
No.
Oh, please try again later. It's not letting me share. Okay, that's odd. Let me try one more time. Is it sharing now?
Yeah, now it's working. Yeah.
Okay, good. All right, so now the risk of having to fly through these again, not so fast. Oh, okay, it was when I discussed the cross sections. There we go. So, yeah, so as I said, the theory cross, this is for DP gamma, the theory cross section was considerably higher. And that would lead to an abundance which is quite a bit lower. Now you say, okay, but if you use the Luna measurement, and there's one group, it's I think it's Pitrou et al., French group, where they've now used the Luna measurement, and they still get a very low measurement. In fact, I don't have the number here, but it might even be a little bit less than this. The problem is, from my perspective, is that they're not using the data for DDP and DDN. So what they're doing is they're using a theory-based cross-section for those two cross-sections. And that's leading again to a very low. And I actually hadn't appreciated it until their recent paper that all three of those cross-sections previously they were using theory-based or theory-corrected, it maybe is better, cross-sections for those deuterium interactions. And if those cross-sections are big, then they get an abundance which is lower. And that's a little bit like this Marcucci rate. Now, this is again for DP gamma, but what that does is that pushes the prediction down relative to the observations. So I think that's all it is. They're using different cross sections. The Italian group, Pesante et al., and our group, we're all using solely experimental cross sections. Now you could argue that the cross sections aren't good, but that's all we have. And if you use those cross sections, the experimentally measured cross sections, then we actually get very good agreement. As you see down here, the Luna themselves did it, and we did it, and again we get essentially the same thing, as do the group by Pesante et al. It's only when you use the higher cross sections for deuterium that you start getting this kind of discrepancy.
Very good. Any other question? So I don't see any other raised hand. So thank you very much, Keith, again for this very nice talk. And I don't know if Stefania wants to say anything.
I just want to thank you, and please send us your slides. We will publish on our website.
Okay, I'll send them to Francesco and.
Sure. No problem.
Okay.
Thanks.
Okay, well, thank you. Hopefully, at some point I can come and visit. I still haven't started traveling yet, really.
Yeah, we hope so. Okay.
Okay, so see you next time to everybody. Bye-bye.
Bye.
Bye.